Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello students, this is lesson 5. Last time you learned about the discovery of the atomic nucleus and the discovery of neutrons. Today you learn about the electromagnetic radiation and the atomic spectra. So first consider the following points. Is it possible to know exactly the location of electron? You know that electrons are always revolve around the nucleus. So is it possible to know exactly the location of electron? Defend your suggestion. Do electrons have a particle nature or a wave nature? Electrons have both particle and wave nature. Explain why electrons does not enter the nucleus even though they are oppositely charged. So these are points to remember before we are going to discuss about the electromagnetic radiation. Electromagnetic radiation. Electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic wave. So electromagnetic wave has two natures, electric and magnetic. Electromagnetic radiation described by two interdependent variables. These variables are frequency and wavelengths. The wavelengths has a symbol lambda in Greek. Wavelengths means the distance between two crests, or the distance between two troughs, the lower case, is known as the wavelengths. So this is one of the components of electromagnetic radiation. So here is a wave. This is a form of a wave. This is the direction of travel. So we have a lambda. The lambda means the wavelengths. Here also we have another wave. So the distance between two crests, we call this uppercase the crest. The distance is known as the wavelengths. In the lowercase also we call it a trough. The distance between these two troughs is also known as a wavelength. Frequency in Greek, the symbol is nu. It is the number of cycles that pass a given point in space per second, expressed unit of per second, or hertz. So here we have an electromagnetic radiation. So here, for example, if you see this is a wave, now the wavelengths decrease in this direction, but the frequency increase. The wavelength is decreasing. For example, if you compare the distance between these two and the distance between these two, we can see that the wavelengths decrease in this direction. But the frequency increase. So when it comes to the energy is increased. Okay? The energy is increased. So for example, here we have different forms of electromagnetic radiation. For example, gamma ray is a form of electromagnetic radiation, ultraviolet ray, infrared, microwave, radio. So for example, if you take gamma ray has here the highest energy, and radio wave has the lowest energy. So for example, here are some forms of electromagnetic radiations. For example, the electromagnetic radiation we used in mobile phones, in radars, even in X-rays. Okay? For example, if you see the visible light is also a form of electromagnetic radiation. Now, here we have an activity. The activity is for you. You'll compare the wavelengths and the frequency of this electromagnetic radiation. For example, we have TV signal, television signal, infrared light, gamma ray, radio wave, microwave, ultraviolet radiation. So TV signal, infrared light, a gamma ray, radio wave, microwave, and ultraviolet radiation. So you will write in increasing order of wavelengths and frequency based on this information. Now, the speed of electromagnetic wave, for example, light, the distance traveled per unit time in meter per second is the product of its frequency, that is cycle per second, and its wavelengths, meter per cycle. That means the speed of the light is the product of its frequency and its wavelengths. The quantum theory of photon. In 1900, Planck hypothesized that energy was quantized. That is, energy can be gained or lost only in a whole number, a multiple of the quantity h nu. So, change in energy is equal to n times h times nu. N means the quantum number, which is an integer. H means the Planck's constant, and nu is a frequency in per second. So we can calculate the change in energy using this formula. For example, calculate the energy in joules of a photon of red light that has a frequency of 3.73 times 10 to the power of 14 per second. What's given is the frequency. The nu is given. The nu is 3.73 times 10 to the power of 14 per second. What is the energy? We know that the energy is H nu. H is the Planck's constant. So the Planck's constant is 6.62 times 10 to the power of minus 34 joule second times the frequency is 3.73 times 10 to the power of 14 per second. So by multiplying these two numbers, we can get the energy of a photon in terms of joule. Okay, the second question is, the photon emitted by a cyclotron has a velocity of 1.50 times 10 to the power of 3 meter per second. What is the wavelength of this photon, given that the mass of the photon is 1.676 times 10 to the power of minus 27 kilogram, and Planck's constant is 6.62 times 10 to the power of minus 34 joule second. So the question is, what is the wavelength? The wavelength is lambda. What is the wavelength? So H is equal to, from de Broglie wave, H over P. H is a Planck constant, P is a momentum. So momentum means simply the product of the mass of the photon times the velocity. So here H is given, that is a Planck constant. The mass is given, and also the velocity is given. So using this formula, we can calculate the wavelengths. The photoelectric effect. So the photoelectric effect is when a light shining on a clean metallic surface can cause the surface to emit electrons. This phenomena is known as the photoelectric effect. So this experiment was done by Albert Einstein. So here we have a phototube. This is a phototube. And here we have a light, incoming light. Here we have a metal surface, that is emitter plate. When a photon bombards the surface of the metal surface, electrons will be ejected, and the electron will come to this side, that is the collector plate. When the electron moves from the emitter plate to the collector plate, means the electron move from one point to another point, they create a current. So this current can be detected by here using the ammeter. Here we have the ammeter. So when there is a flow of electron from the emitter plate to the collector plate, the ammeter will deflect. The ammeter will deflect. That means there is a current. There is a current means there is a movement of electron from the emitter plate towards the collector plate. Okay. So this is known as the photoelectric effect. So photoelectric effect experiment emphasize the following key points. 1. Light shining onto the surface of a metal is capable of ejecting electrons. Okay? When a light falls on a metal surface, it can eject electrons from that metal. The second one is the electrons that are emitted come off at energies depends on the frequency. This is very important. It depends on the frequency, but not on the intensity of the light. The electrons that are emitted come off at energies depends on the frequency, but not the intensity of the light. If a photon has sufficient energy, then the electrons will be emitted. Okay? The electrons will be emitted. If a photon has more than minimum energy, minimum requirement, so the excess energy appears as kinetic energy of the emitted electrons. So using this idea, we can develop a formula. That is, we have H nu. H nu means the photon energy is equal to the kinetic energy of the ejected electron plus the binding energy of the electron in the metal. We know that the kinetic energy can be calculated, the kinetic energy of the electron can be calculated as using half times the mass of electrons times the velocity of the electrons square, and the binding energy of the electrons can be calculated as H times nu. So this one is the threshold frequency. So by substituting this one, we will have H nu is equal to H nu naught plus half mass of electrons times the velocity of the electrons square. So here is the question. The threshold frequency for the metal potassium is 5.46 times 10 to the power of 14. Here is 10 to the power of 14 per second. Calculate the maximum kinetic energy and the velocity of that emitted electron has when the wavelengths of the light shining on the potassium surface is 350 nanometer. We can change 350 nanometer into meter. Nano means, by the way, 10 to the power of -9. So using the above equation, you can solve this equation. Students, thank you for following me. Next time, we'll continue lesson 6.